My name is James, and I'm from the User Systems Group at the NCCS. And at the NCCS, our leadership computer is the Titan supercomputer. So, okay, put on Titan. Look, so Titan 9% of its power from the GPU, the NVIDIA Kepler. This is attached to the CPU by a PCIe. So node typically looks like, or all like. Okay, so the sample code I'm going to be using here is just a very simple Monte Carlo operation to find pi, just to estimate pi. And we know from geometry that ratio of the square and the circle of radius 1 is pi over 4. So we can use this, and basically what we're going to do is we're going to scatter a number of random darts at the circle and square. And we're going to take the ratio of how many darts actually land in the circle and how many darts, and the total number of darts that we throw, and multiply it by 4, and we can have our pi. And the closer to an infinite number of darts that we throw, the better, closer to pi you'll reach. This is what it's going to look like, but basically, ideally on an infinite scale. Okay, so I chose this is because the Monte Carlo method is very embarrassingly parallel. And parallel, I mean that each of the operations it takes to find test if it's in the circle can be done completely independently of all the other points. So no data between what's going to end up being iterations of the report. Okay, so this is what we want to do is we want to initialize our count variable to 0, and this is going to keep track of how many points lie in that curve. And we set up our for loop, and we want it to loop until however many darts we want to throw. And in cases, I tend to go for 1%. That gives really good estimation. Okay, I'll just point out that this code, this algorithm, will only calculate for one quadrant, but the symmetry of it, we can go ahead and just treat it as a whole circle. As this loop goes through this loop, each iteration will find exactly one point. So one point after the other, after another, until it's 100,000. Okay. So the of this loop is going to find an X and a Y value. This is going to use the standard C provided by C. Okay. And then we get if this is inside the circle or if it's not. And if it's not, then we'll go ahead and increment our count. And then finally, once this loop's done, we simply take the ratio and multiply by 4. That'll give us our rough estimation of pi. So basically, our goal in writing our code is to divide our code into parts that will execute on host and parts that will execute on device. Host being the CPU, device being GPU. Our CPU code is basically what's going to be in our main function as runs on the host that sets the GPU up for our kernel to be launched. And kernel is basically the function that we want to run on the GPU in parallel to compute our data. And an ideal example is, like I showed you before, is this for loop that where all iterations are can be completely independently done. Okay, so to take it from there, we want to profile our code, and we want to look at it, and we want to see what part of it actually is most intense, computationally intense, and takes long. And that's where we want to concentrate most of our efforts in accelerating our code. So tool at OLCF for profiling is CreatePathFly. This is just one of the tools. This is used for profiling your CPU code to help you figure out where you need to focus acceleration. And this also offers the NVIDIA Visual Profiler for the toolkit for profiling your GPUs to optimize once you have them written. I'm not going to go into using NVIDIA Visual Profiler at all because we're concentrating now on getting our serial code and accelerating. The serial code run through CreatePath Lite, and it gives you some basic information like how many nodes it's used, how many threads it wants, how long it took, etc. And then have this second table of output, and it'll show you what percentage of the time and power is being where. And as you can see, where RAM is being used is where most of our effort. That's 60% of our power is being used right there. So our okay, we want to analyze this code, and we want to see, like I said, the RAM section. We want to accelerate that, and it's what's most computationally intensive as well as what takes the longest and part of your program. Structures that you'll find, like one for instance, is loops, and you specifically want to look for loops with no dependence between data. Okay, you run into some challenges when some of which are the fact that you have to manually allocate memory not only on the host side, the CPU side, you also have to allocate and manage your memory on the CPU side. And you also copy that memory back and forth. You have to copy the kernel to the device and copy back your resulting data that you computed. And also, and when you want to make sure that it's worth the time and the effort to copy all this to the device and do all this on the GPU, the device. And because communicating with the device over the PCI bus is overhead when you're communicating. So ways you can accelerate your code. Three I'm going to go over mainly are OpenACC, CUDA, and Rust. These are the only ways, but they are what I can do. Okay, so what's we got our portion of copy this to the kernel to be able to the so this communication over the PCI. So that's some overhead right there. So the kernel's been launched, and once it's finished computing the data, you want to copy that data back to the host. So that communication over the PCI. So you got to keep that in mind. There's going to be a lot of overhead associated with all of that. Okay, OpenACC is probably one of the simplest ways you can accelerate code, but it can also lead to some trouble. Okay, OpenACC is similar to OpenMP. I believe there's some presentations on OpenMP. It uses the compiler directive as versus the compiler directive to tell the code to accelerate the closed section enclosed by curly. And the compiler will look at this and figure out the best way to accelerate this code and manage all copying to the device. So, like I said, it tends to be a higher level kind of acceleration API. Also, will have the explicit initialization of the accelerator, allocation, memory copying. You won't worry about it. You really would. You can take your serial code and accelerate it very fast using OpenACC with very little editing of your code. There's a need for the programmer to manage separate variables for the CPU and separate variables for the GPU. And one of the drawbacks of using OpenACC is there are very few compilers available that actually implement OpenACC standards. Two of which are available at the OLC step is CGI compiler and the Crank compiler. As of right now, there are no free compilers that implement the standards, so keep in mind. Okay, so what we first want to do when we're accelerating our code is because we can't run functions inside of a kernel, we can't run RAM. So we need to pre-fill an array of random numbers, 2 times however many points or however many darts we want to throw, because we don't want a value. And so we did a fill this array with random numbers. And then, like we've already done, we need to identify the region of code to accelerate with OpenCV. And then include the copy in, because we need to copy in the full array of random numbers to the device, to the accelerator. And this is going to look like. Like before, we want to initialize count to 0. Then we want to just go ahead and fill our random numbers array with random numbers that are by just calling random. Okay, next practice. It's very simple, straightforward. Just pragma ACC intel region. And we want to get in this whole array of 200,000 random numbers and copy this to the accelerator. This is the actual what forms the Monte Carlo operation. This loop is going to be broken up by the compiler. Each iteration will be executed in parallel with all the other. And so it'll launch that as its own kernel to perform the Monte Carlo operation. And it's very similar to the previous code. The only differences being it loads the random numbers from the array instead of calling rand, and as well as it loads the value of z, in this case, into the array. Okay, is the compiler needs a second for loop, and it'll take the second for loop to make another kernel of it, a reduction kernel, a kernel for reduction. And so, depending on if this is less than or equal to 1, then we'll go ahead and increment count and say that that this point isn't the kernel. And then later on, we can use that once we get out of our parallel region, use that to compute our pi. And so, as we saw in the previous serial example, we do 1 point and we go on to the next. Well, since this is self, it'll obviously do 7 points at a time on parallel instead of one after the other. CC code is very straightforward. You can Python with the CPI compiler. You just go to the CUDA toolkit, and you want to make sure you go with the capital CC compiler. You'll just use the -ACC flag. There are other flags available to give you more information about how the compiler is accelerating your code or targeting different platforms, etc. But you really need to make sure you have the -ACC flag. Print flag load module. It's a pretty specific module in this case, but it's the same idea. Use the capital CC compiler, and instead of -ACC, you use the -H pragma, and that you need for compiling. And the thing to note is if you don't compile it with your -ACC or -H pragma ACC, then it'll run in serial code. And that can be used as a really nice debugging. Okay, we have CUDA. CUDA is the language that the NVIDIA GPUs go by. So you have your thread model, or the CUDA thread model. It's interesting. You have your CUDA kernel, and the CUDA kernel, like I said before, is basically just a function that the threads execute in parallel. And there's your threads, which is just a parallel instance of your kernel. So, about this is you have thread blocks, and thread blocks are groups of threads that execute the same instructions simultaneously, and also share a common shared memory space. Those blocks are grouped as grids, and that is of how you're launched on the accelerator. Okay, there's a hierarchy of memory. You have your thread private memory, which is the fastest access. And then this is hosting the registers on the GPU. So next you have your memory, which is all the threads in a block, and this memory resides in cache on. And then your global memory, which is your GPU RAM. This is not your CPU RAM. They're not the same memory space at all. But every thread from any block can access this global memory space, but it is very slow and very expensive. Okay, so an outline of what our CUDA accelerated code is. Firstly, memory on the device that is going to hold our random numbers as RAM. So we need to using CUDA. Generate random numbers using a library that CUDA provided a library called cuRAND. Because again, we can't launch on the device. And we're to launch our Monte Carlo kernel, and we're just going to copy the results back to the host. Okay, good enough. The same way you would use that. Literally no difference there. We want to create an array for both our X and our Y random numbers. And we also want an array for our computed data. And I want to mention here that the underscore D and underscore F or H convention is commonly used to tell the pointer the array lies on the device or if it lies on the host. Functions are called inside your CPU code in your main, and they're not called from your kernel at all. And this is a communication over the PCIe bus, so it's going to have a lot of overhead associated. When you're accelerating. Okay, it provides this really nice library for producing high-quality random numbers. And essentially, by calling these functions, it will launch a kernel on the GPU to create these random numbers. It's very similar. You just create the random number generator. You want to feed it with a fairly random value, time, etc. And then we finally want to launch it. We don't actually launch it by one for X and one for Y to fill those arrays. And then we can go ahead and destroy our and all this code is called from your host code main function. This is not from your GPU code. This is what our kernel looks like. It looks very similar to we've previously seen with the difference. The first you'll notice is the global vector. This is simply just appended to the beginning of the function, and to tell her that this is going to be a this is kind of where a lot of people tend to hang on the global thread ID of your, and we did in order to find the numbers associated with it. To find this global thread number, we want to take the size of the block. So in this case, in this image, it's going to be 6 threads, and we want to take the block number, and then we want the thread number, the local thread number from within that block, a thread 1. And so we want to multiply the block size times 1, the block ID, and then we want to go ahead and add what the thread number is, and that will be the global thread number of the thread on launched by your kernel. Okay, and so when that we're accessing, if value comes up to 7, we simply load in whatever 7 above the array to our into our X and our Y value for our guards. Okay, and then what we do is we just compute to see if it's in the circle, and if it is, we're going to load a 1 into our count D array, and if it's not, we're going to load a 0. And so that I do this so that when you reduce on the host, it reduces down to however many points we're at. A kernel is similar to calling a function, except for the fact of the addition of the CUDA notation. Triple brackets, you want to say how many threads per block you want, and then write a comma. You want to say how many blocks you want, and that's how you launch a CUDA kernel. And again, the communication over the PCIe.
Is there a limit to how many threads or blocks I can launch at one time?
I'm not sure the exact number. It varies GPU to GPU.
So at the versus
yeah. and then that's in your point. And like I said, the communication over the PCI and stuff. So in mind, there's some overhead communication. Okay, and our kernel is finished. We want to go ahead and copy back our count array and store it into an array on the device. Or on the array. Okay, done with a CUDA. A CUDA is very similar to the C's memcopy function, except that we have one last parameter that we want to pass it, saying that we want the direction of the copy. We either copy it from the device to the host or the host to the device. And then we want to copy it from the device. So into root host. And finally have a reduction to sum it all up. And then we want to use that value, reduce count, and we use that in our estimate. CUDA code is very simple. The NVCC compiler is available with the CUDA SDK. You have to first load the CUDA toolkit on Titan and just use NVCC to compile it instead of your standard CC. They're available to target it to specific types of NVIDIA GPUs. They're not always necessary. Now we get to the interesting part. We have Thrust. Thrust is completely different from all the other methods we've looked at so far. Thrust is a template library provided for the GPU. It imitates the C++ standard template library, which is solely for CPU. This will accelerate either pre-accelerate functions, or it provides pre-accelerated functions that will store, reduce, transform your data using the device. And this is in the CUDA toolkit 4.0. If you have C++ code, it's very easy to take if you're reduction using your C++ code, then you can just use the Thrust reduction instead. So it's very easy to code and accelerate it that. So it's just all right. So what we first do is we want to declare a kernel of the Carlo operation inside of a struct. If you're not familiar with a struct, it's similar to a C++. What we'll do is we want to use Thrust. And Thrust provides a really nice random number generator function that we can use. We actually call this from our kernel. So we want to use Thrust and we want to feed it and feed our random number generator and generate our random numbers for our and we want to launch 100,000 threads. And we want to increment our counter for however many points actually inside the circle, and we want to keep track of our 100,000 points that we've actually calculated. As all the other examples, each thread is going to calculate the value for 1 point exactly. Okay, and all this by a somewhat cryptic way from our CPU code, all this kernel.
So we get different into or
to my knowledge, it's just whatever you want to do. As for your
the same time, you use
it's completely different, to my knowledge. So you can actually, instead of using Thrust here, you can use the Boolean library if you really wanted to, but in this case, it just Thrust is yeah. It depends on your application.
And maybe a follow-up to that. So, like something like Google allocation, how do you different between allocation of memory through the Google Cloud and regular way of Google Maps?
I'm not sure at this point. That's a little bit more.
Everything else covers, except you're using a virtual wallet to work and everything in the data.
So basically, we're going to.
Mhm. So, this is what our kernel is going to look like. We're going to define the function inside. We're going to refer to this as the name of our struct. We're going to refer to the kernel as our struct for now on. Okay, to define and we use the host and the device to tell the compiler that this is going to be this function is a kernel. Okay, and next and to provide our random number. So what we do is we just need to set up a random number generator and as a distribution from the 0 because of our circle radius 1. And so we just like this in order to get our random x and our random y value. And we calculate to see if it's inside of the circle or not, and increment count, and ultimately count, since this is just 1 point, ultimate count will either be a 0 or a 1, and it's going to return that. Each thread will return a value. The reason that happens is because the way we launch our kernel is we launch it through a thrust function. We launch it transform reduce. So when we do this, we want to say that we want to launch 1,000 threads. We want to say our first thread is going to be thread 0, our second thread is going to be in dark or 100,000. We want to pass it our Monte Carlo operation, and from that operation, every thread that returns that either 1 or 0, it will be reduced on top of that 0 that's seeded there. It will be reduced into our final count variable, which will hold however points are actually at that circle. And then that's to inoculation of our estimation. Okay, code. You would load the CUDA toolkit and use MVC to so kind of in summary, each of these methods has its good and its downside. OpenAC has very simple syntax. It hides all of the memory initialization, the copying of the memory to and from the device, and the compiler does most of the optimization work for you. It'll break down those for loops into threads and all that behind the scenes for you. But it's only supported on very few compilers. You've got to say. And it can be notoriously difficult. CUDA gives you a high amount of control over your code. It's very well. It's been around for a while. It's own NVCC compiler, so you don't have to worry about is this compiler compatible with it. It comes with many libraries like the QRandom library or the QBlock that are available with the CUDA toolkit. But it can be a pain to manage all of the separate variables for the CPU and for the GPU, as well as copying the data back and forth from the device. And CUDA works on NVIDIA GPU. So if you have an API, you can get so you have Thrust. Thrust it imitates the C++ and the template library, and it means pre-accelerated commonly used functions like reductions, number generation, like I use, sort, etc. And you can define your own kernel functions if you want to set. And for those who are unfamiliar with templates and standard template libraries, this can be kind of confusing. So that's kind of one of the downsides. And it's kind of got somewhat of a cryptic way to compare to CUDA, where you explicitly launch your kernel and break it out very quickly. Okay, so all these here can be found on the LCS GitHub, if anybody's interested. We all have an accelerated computing guide on the LCS website. So a lot of there's GPU computing support found on the website as well. And that being said, are there any questions?